Right now, something impossible appears to be happening above your head. At this very moment, the sun is releasing more energy than billions of nuclear bombs exploding every second. Its core is hotter than 15 million degrees Celsius. Its gravity is so powerful that it contains more than 99% of all the mass in our solar system. And yet, despite all this violence, the sun appears calm, predictable, reliable. Tomorrow morning, it will rise again. Next year, it will still be there. 1,000 years from now, it will probably look exactly the same. In fact, the sun has remained astonishingly stable for nearly 5 billion years. That should bother us, because everything we know about nature seems to suggest that such stability should be difficult. A fire eventually burns out.
An explosion eventually fades. A machine eventually breaks. Nothing lasts forever. So why does the sun? What prevents this gigantic sphere from collapsing under its own immense weight? What prevents it from exploding uncontrollably? Why does it produce almost exactly the right amount of energy, year after year, century after century, million year after million year? And perhaps most mysterious of all, why does the universe allow such an object to exist in the first place? The deeper scientists looked into the sun, the stranger the mystery became. The answer would eventually involve gravity, quantum mechanics, nuclear physics, relativity, and some of the most remarkable coincidences in nature. Because hidden inside the ordinary sunlight that falls on your skin is one of the greatest balancing acts in the known universe.
And if that balance were changed by even a tiny amount, stars like our sun might never have existed at all. To understand why the sun is so stable, we first need to appreciate how unstable it should be. Imagine gathering almost every object in the solar system into one place. Every planet, every moon, every asteroid, every comet. Now combine all of them together. Even then, the result would still be only a tiny fraction of the sun's mass. The sun contains approximately 1.989 times 10 to the 30th kilograms of matter. That is a number so large that it becomes almost meaningless to human intuition. What matters is what that mass does. Mass creates gravity, and the sun possesses an enormous amount of it. Every single second, the sun's gravity pulls inward on every layer beneath it. The outer layers pull on the inner layers pull on the core. The entire star is constantly trying to squeeze itself smaller. If gravity were the only force involved, the sun's fate would be simple. It would collapse. The entire star would begin falling inward. Its radius would shrink. Its density would increase. Its temperature would rise. And eventually, the sun would become something very different from the gentle star we know today. This idea may sound strange at first. When we look at the sun, it does not appear to be falling. But according to astrophysics, the sun is, in a sense, always trying to fall inward. Gravity never stops pulling. Not for a second. Not for a millisecond. Not once during the entire history of the solar system.
This realization creates our first major mystery. If gravity has been trying to crush the sun for billions of years, why has it not succeeded? The question becomes even more interesting when we look back in history. For much of human civilization, nobody knew what powered the sun. People naturally assumed it was some kind of fire. After all, what else could produce heat and light? But during the 19th century, scientists began encountering a serious problem. Ordinary burning could not explain the sun. The numbers simply did not work. Even if the sun were made entirely of the best chemical fuel imaginable, it would only shine for a few thousand years before exhausting itself. Yet geological evidence suggested Earth was far older than that. Later, evolutionary biology required hundreds of millions of years. Eventually, the evidence pointed toward billions of years. The sun seemed trapped inside a contradiction. It was clearly producing enormous amounts of energy, yet no known energy source could keep it shining long enough. This became known as the solar energy problem. Some of the greatest scientific minds of the 19th century struggled with it. Among them was Lord Kelvin. Kelvin proposed that the sun might be powered by gravitational contraction. As the sun slowly shrank, gravitational energy would be converted into heat. This was actually a brilliant idea, and for a while it appeared promising. But eventually it failed too. The calculations showed that gravitational contraction could power the sun for only tens of millions of years, not billions. The mystery remained unsolved.
Nature seemed to be hiding something. The answer would not emerge until scientists began uncovering an entirely new layer of reality, a layer hidden deep inside the atom itself. At the beginning of the 20th century, physicists were discovering that matter was far stranger than anyone had imagined. Atoms were not indivisible. Inside them existed smaller particles. Inside those particles operated forces unlike anything seen in everyday life. The familiar world of chemistry was only the surface. Beneath it lay nuclear physics. And somewhere within that hidden realm was the secret of the sun. But before scientists could understand how stars work, they first had to understand something even more fundamental: why matter itself contains so much energy. In 1905, a young patent clerk named Albert Einstein published a revolutionary idea. One equation would eventually transform our understanding of stars. E equals mc squared. Most people recognize the equation. Far fewer appreciate how astonishing it truly is. The equation says that mass and energy are not separate things. Mass is a form of energy: locked energy, condensed energy, stored energy. And because c, the speed of light, is extraordinarily large, even a tiny amount of mass corresponds to a tremendous amount of energy. This was the first major clue. Perhaps the sun was not powered by chemistry. Perhaps it was powered by mass itself. If that were true, the sun suddenly possessed access to an energy reservoir far larger than anything 19th century scientists had imagined. But another mystery immediately appeared. Even if mass could become energy, how exactly was the sun performing the conversion? What process inside the star was making it happen? And why was that process so stable that it could continue for billions of years without either stopping or running out of control?
The answers would force physicists into one of the strangest realms of science, a realm where particles pass through barriers they should not be able to cross, a realm where probability replaces certainty, a realm where the existence of stars depends on events that classical physics says should be impossible. To appreciate how strange the sun really is, imagine two positively charged particles approaching one another. According to classical physics, they should repel. The closer they get, the stronger that repulsion becomes. It is the same reason two identical poles of a magnet push away from each other. Inside the sun, the primary fuel consists of hydrogen nuclei, which are simply single protons. Every proton carries a positive electric charge. That means every proton repels every other proton. Immediately, a problem appears. If the sun is powered by combining hydrogen nuclei together, how can they ever get close enough to touch? The temperatures in the sun's core are extraordinary by human standards, reaching approximately 15 million Kelvin. The particles there move at enormous speeds. They collide constantly.
Yet even those tremendous temperatures seem insufficient. Classical calculations suggest that most collisions should fail.
The electric repulsion should prevent fusion from occurring efficiently. In other words, by the rules of ordinary physics, stars should barely work. This became one of the most important puzzles in astrophysics. Scientists knew the sun was producing energy. They knew nuclear reactions were involved, but the numbers refused to cooperate. The particles simply did not seem energetic enough. Then quantum mechanics entered the story. Quantum mechanics is often described as strange, mysterious, or counterintuitive. In this case, those descriptions are not exaggerations. Deep within the microscopic world, particles do not behave like tiny billiard balls. Instead, they possess wave-like properties. And because of those wave-like properties, nature occasionally permits something extraordinary. A particle can appear on the other side of an energy barrier that it seemingly lacks the energy to cross. Physicists call this quantum tunneling. The name sounds technical. The reality sounds impossible. Imagine rolling a ball toward a hill. If the ball lacks sufficient energy, it rolls back down. That is what common sense expects. But quantum mechanics sometimes allows the ball to appear on the opposite side anyway. Not because it climbed over, because reality itself operates according to probabilities rather than certainties at extremely small scales. Inside the sun, this effect changes everything. Most hydrogen nuclei do not possess enough energy to overcome their mutual electric repulsion. Yet occasionally, through quantum tunneling, they get close enough for another force to take over, the strong nuclear force. Unlike electromagnetism, which pushes the protons apart, the strong force acts at extremely short distances and pulls particles together with tremendous strength. Once two nuclei come sufficiently close, the strong force overwhelms the electric repulsion. Fusion becomes possible. The remarkable consequence is that the sun shines because of events that classical physics alone would never permit. Every ray of sunlight reaching Earth ultimately owes its existence to countless quantum tunneling events occurring deep inside the solar core. Reference: pioneering work by George Gamow helped establish the importance of tunneling in stellar fusion. Now comes an even deeper surprise. Most people imagine the sun as an enormous furnace consuming fuel as rapidly as possible. The reality is almost the opposite.
The sun is extraordinarily conservative. Fusion in the core occurs at a surprisingly slow rate. If hydrogen fused much more rapidly, the sun would burn brightly, but briefly. Its lifetime might be measured in millions rather than billions of years. Complex life on Earth would almost certainly never have emerged. The reason the sun survives for billions of years is precisely because fusion proceeds so reluctantly. Nature has arranged a remarkable balance. Fusion occurs often enough to support the star against gravity, yet slowly enough to prevent rapid destruction of its fuel supply. This delicate behavior is one of the keys to stellar stability. In fact, if you could somehow take a small spoonful of material from the sun's core, it would not behave like a gigantic hydrogen bomb. The energy generation rate is surprisingly modest. Per unit volume, the human body actually produces energy through metabolism at a rate comparable to or greater than some regions of the solar interior. That statement sounds absurd, yet it is true. The sun's immense luminosity arises not because each part of it is producing energy at a spectacular rate, but because the star is unimaginably large. Billions upon billions of cubic kilometers contribute simultaneously. The result is a total power output of approximately 3.8 times 10 to the 26 watts every second for billions of years. And still the mystery.
Because generating energy is only part of the problem. The sun must also regulate itself. Suppose fusion suddenly increased. what would happen? At first glance, more fusion sounds harmless. More fusion means more energy. More energy means more pressure. But pressure changes the structure of the entire star. As additional energy accumulates, the core expands slightly. That expansion reduces density. A lower density means fewer particle collisions. Fewer collisions reduce the fusion rate. The system naturally begins correcting itself. Now imagine the opposite. Suppose fusion decreases. Less energy means less pressure resisting gravity. The core contracts slightly. As it contracts, temperature and density rise. Higher temperatures increase the likelihood of fusion. Fusion accelerates again. Once more, the system corrects itself. The sun behaves almost like a cosmic thermostat. Not because it possesses intelligence, not because it follows instructions, but because the laws of physics naturally create feedback mechanisms. The star continually responds to disturbances in ways that restore balance. This phenomenon forms the foundation of stellar stability. Astrophysicists call the overall condition hydrostatic equilibrium. Gravity pulls inward. Pressure pushes outward. Neither side completely wins. The star exists in a state of dynamic balance. The word equilibrium sometimes creates the wrong impression. It sounds static, motionless, frozen. The sun is none of those things. The sun is extraordinarily active. Plasma circulates. Magnetic fields twist. Particles collide. Fusion reactions occur relentlessly. Shockwaves travel through stellar material. The entire star vibrates. In fact, scientists study subtle oscillations on the sun's surface using a field known as helioseismology. Just as earthquakes reveal the structure of Earth's interior, solar vibrations reveal conditions deep inside the star. Reference extensive helioseismology research has confirmed theoretical models of solar structure with remarkable precision. The picture that emerges is not a quiet object. It is a controlled storm. A vast sphere of turbulent plasma maintaining stability despite unimaginable internal violence. And that stability becomes even more impressive when we consider the scale of time involved. Human civilizations rise and fall in thousands of years. Recorded history spans only a few thousand years. Agriculture emerged roughly 10,000 years ago. The sun has remained stable for nearly 4.6 billion years. The ratio is almost incomprehensible. If the entire history of civilization occupied a single second, the sun's age would stretch across many days. Long before the first cities. Long before mammals. Long before dinosaurs. Long before complex life itself, the sun was already shining. And through all those ages, gravity continued pulling inward. Fusion continued pushing outward. The balance endured. Yet there remains a deeper question. Why does this balance point exist at all? Why should the laws of nature permit stars to find stable configurations? Why not universes where gravity always wins? Or universes where fusion always runs away uncontrollably?
To answer that, we must look beyond the sun itself and examine the fundamental constants of nature. The investigation is about to move from astrophysics into one of the most profound questions in modern science. Because hidden behind the stability of every star lies an astonishing fact. The universe appears to operate within an extremely narrow range of possibilities. And if those possibilities were even slightly different, the night sky might contain no long-lived stars whatsoever. Imagine possessing the ability to redesign the universe. You are allowed only one change. Not a dramatic change. Not 100 times stronger, not 1,000 times weaker. Just a tiny adjustment to one of nature's fundamental settings.
At first, it seems harmless. After all, how much difference could a small change really make? The answer, astonishingly, might be everything. Because the sun does not exist simply because hydrogen exists. It does not exist simply because gravity exists. It exists because numerous physical laws cooperate within an extremely specific range. Change those laws enough, and stars may never form. Or they may form only briefly before destroying themselves. The stable sun hanging above Earth may be far more fragile than it appears. To understand why, we need to discuss something physicists call fundamental constants. These are numbers built into the fabric of reality. Unlike the speed of a car or the temperature of a room, fundamental constants do not depend on circumstances.
They appear to be woven into nature itself. Among them are quantities that determine the strength of gravity, the strength of electromagnetism, and the strength of the nuclear forces. Every atom, every molecule, every planet, every star, every galaxy depends on these values. The sun is no exception. Consider gravity first. Gravity is actually the weakest of the known fundamental interactions. That statement often surprises people. Gravity dominates our daily experience. It keeps planets in orbit. It shapes galaxies. It governs stars. Yet, on the scale of elementary particles, gravity is astonishingly weak. A small refrigerator magnet can overcome the gravitational pull of the entire Earth on a paperclip. And yet this apparent weakness may be one reason stable stars can exist. Suppose gravity were significantly stronger. Hydrogen clouds would collapse more aggressively. Stellar cores would become hotter. Fusion would proceed more rapidly. Stars might burn through their fuel much faster. Some theoretical studies suggest that stronger gravity could dramatically reduce stellar lifetimes. The universe would still contain stars, but many would live shorter lives. A star surviving for billions of years might become much rarer. Now imagine gravity becoming weaker. The opposite problem emerges. Gas clouds may struggle to collapse efficiently. Some stars might never reach the temperatures necessary for sustained fusion. The balance begins disappearing from the other direction. Somewhere between these extremes lies a narrow region where long-lived stars become possible. The sun occupies that region. But gravity is only part of the story. Even more remarkable is the role played by the strong nuclear force. This force operates inside atomic nuclei. It binds protons and neutrons together. Without it, atomic nuclei would immediately fly apart. No carbon, no oxygen, no iron, no planets, no biology, no stars as we know them. Yet the strong force cannot simply be arbitrarily strong. If its strength were altered significantly, the entire chain of nuclear reactions inside stars would change. The production of chemical elements could become radically different. Many of the atoms required for complex chemistry might never appear. The universe could become sterile. In the 20th century, physicists discovered something extraordinary about carbon production in stars. When stars fuse helium nuclei together, they create carbon through a sequence of reactions that depends on a very specific resonance. This resonance was predicted by astrophysicist Fred Hoyle before it was experimentally confirmed. Hoyle realized that without this resonance, stars would produce very little carbon. The existence of carbon-based life seemed to require an incredibly fortunate arrangement within nuclear physics. Whether one interprets this as coincidence, necessity, selection effect, or something deeper remains debated, but the fact itself remains remarkable. The chemistry of life appears linked to delicate details inside stellar interiors. And suddenly, the sun no longer looks like an isolated object. It becomes part of a much larger story.
A story connecting nuclear physics to biology, quantum mechanics to astronomy, the microscopic world to the macroscopic universe. Now, consider another astonishing feature. The sun is not merely stable, it is self-regulating across immense spans of time. Over billions of years, its luminosity changes only gradually. That does not mean it never changes. In fact, the young sun was slightly dimmer than today's sun. Models indicate that early in its history, solar luminosity was roughly 70% of its current value. This creates a fascinating puzzle known as the faint young sun problem. If the sun was significantly dimmer billions of years ago, Earth should have been frozen. Yet geological evidence indicates the presence of liquid water. Rivers existed. Oceans existed. Life eventually emerged. Somehow Earth's climate remained suitable despite receiving less solar energy. Scientists believe atmospheric conditions played an important role. Higher concentrations of greenhouse gases may have compensated for the reduced solar output. What matters for our story is that even this apparent paradox highlights the extraordinary interplay between stellar evolution and planetary conditions. A slightly different sun, a slightly different atmosphere, a slightly different history, and Earth might have followed an entirely different path. The deeper we investigate, the less inevitable everything appears. The sun begins to resemble the result of countless interconnected processes balancing one another across cosmic timescales. Yet there is an even stranger realization waiting ahead. The sun is not stable because it has found a perfect state. The sun is stable because it is constantly changing. That sounds contradictory,
But it reveals one of the most important truths in astrophysics. Nothing in the universe remains exactly the same. Not planets, not stars, not galaxies, not even space itself. The sun survives precisely because it evolves. Every second, approximately 600 million tons of hydrogen undergo fusion in the solar core. Roughly 596 million tons become helium. The remaining mass is converted into energy, according to Einstein's relation between mass and energy. The difference is tiny compared with the sun's total mass, but over billions of years, the effects accumulate. The composition of the core gradually changes. Helium builds up. Hydrogen becomes less abundant in the central regions. The sun slowly adapts to these changes. As helium accumulates, the core contracts slightly. That contraction raises temperatures. Higher temperatures increase fusion rates. As a result, the sun slowly becomes brighter over time. The process is extraordinarily gradual. Human beings cannot perceive it. Entire civilizations cannot perceive it. But astrophysics can. When scientists compare stellar models with observations of stars at different stages of evolution, the pattern becomes clear. The sun today is not identical to the sun that illuminated Earth billions of years ago. It is the same star. Yet it is also a different star, a slightly hotter star, a slightly brighter star, a slightly older star. And that means stability does not mean permanence. It means controlled change. The sun survives because its evolution unfolds slowly enough to maintain equilibrium while continuously adapting. This idea appears throughout nature. A bicycle remains upright not because it is motionless, but because it is moving. A living organism remains alive not because nothing changes, but because countless processes continually adjust to changing conditions. Likewise, the sun remains stable because it is constantly responding to its own evolution. The balance is active rather than passive, dynamic rather than static. And once we recognize this, another question naturally emerges. If the sun has remained stable for 4.6 billion years by continuously adjusting itself, what ultimately limits that process? Can this balancing act continue forever? Or is there a moment, hidden somewhere in the future, when gravity finally wins, fusion finally changes, and the stability that has endured for billions of years begins to unravel?
To understand what ultimately limits the sun's stability, we need to look beyond its present condition and follow its entire life cycle. Because stability in a star is not a permanent property. It is a phase. A long one, but still a phase. Right now, the sun is in what astronomers call the main sequence stage. This is the long middle period of a star's life, where hydrogen fusion in the core is sustained in a relatively steady way. But steady does not mean unchanged. It only means slowly evolving while maintaining balance. And that balance is supported by a very specific internal structure. At the center, hydrogen nuclei are fusing into helium. Above that, layers of plasma transport energy outward. At the surface, that energy finally escapes as light and heat. But this structure depends on one crucial condition. Hydrogen must remain abundant in the core. As long as hydrogen is present, fusion continues in a controlled way. But that supply is not infinite. Every second, the sun converts millions of tons of hydrogen into helium. Over billions of years, helium accumulates in the core, like ash in a furnace. And this changes everything. Helium is heavier than hydrogen.
It does not fuse under the same conditions as easily. So as helium builds up, the core becomes progressively less efficient at generating energy. At first, this seems like it should weaken the sun. Less fuel means less energy. Less energy means less pressure. Less pressure should allow gravity to compress the star. And that is exactly what begins to happen. But here is where something counterintuitive occurs. As the core contracts under gravity, it does not simply become denser, it becomes hotter. This is a direct consequence of gravitational compression. When matter is squeezed inward, particles move faster. Faster motion means higher temperature, and higher temperature increases the rate of nuclear reactions in the surrounding hydrogen shell. So even though the core is becoming less active, the region around it becomes more active. A shell of hydrogen outside the core begins to fuse more intensely than before. The sun does not die suddenly. It redistributes its energy production. This marks the beginning of a dramatic transformation. The sun will eventually leave the stable configuration we observe today. It will expand, not contract, expand. As the outer layers absorb energy from the intensified shell fusion, they begin to inflate outward. The surface cools slightly, but the total size increases enormously. The sun will enter what is known as the red giant phase.
During this stage, it will grow so large that it could engulf the inner planets. Mercury will almost certainly be consumed. Venus will likely be destroyed. Earth's fate is less certain, but even if it avoids direct engulfment, it will be rendered uninhabitable long before that point. This transformation is not a failure of stability. It is the natural consequence of a star exhausting its primary fuel source. What we call stability is always temporary equilibrium between competing forces. And when the underlying conditions change, the equilibrium shifts. But something even more interesting is happening beneath this transformation. Inside the sun's core, a new kind of pressure begins to matter. Not thermal pressure, not fusion pressure, but quantum mechanical pressure. When matter is compressed to extremely high densities, electrons resist being forced into the same quantum state. This is known as degeneracy pressure. It arises from the Pauli exclusion principle,
one of the fundamental rules of quantum mechanics. No two electrons can occupy identical quantum states simultaneously. So as gravity squeezes matter further, electrons push back. This form of pressure does not depend on temperature. It depends only on quantum statistics, and it becomes crucial in the final stages of stellar evolution. If a star is not massive enough to overcome this quantum resistance, it will eventually stop collapsing and stabilize in a new form, a white dwarf. This is where the story of stellar stability takes an even deeper turn, because now we see that stars are not simply held up by heat from fusion.
They are also supported in their final stages by the structure of quantum mechanics itself. For more massive stars, even electron degeneracy pressure is not enough. Gravity eventually wins again. In those cases, matter is crushed further until electrons and protons combine to form neutrons. A neutron star is born. Here, yet another form of quantum pressure emerges: neutron degeneracy pressure. Again, the same principle appears. Nature resists compression through quantum rules that prevent identical states from stacking infinitely. At every stage, a different balance is reached. Main sequence stars like the Sun rely on fusion pressure. White dwarfs rely on electron degeneracy pressure. Neutron stars rely on neutron degeneracy pressure. And if even that is exceeded, collapse continues toward a black hole. What this reveals is something profound.
Stability in the universe is not a single mechanism. It is a hierarchy of mechanisms, each one activated when the previous one fails. The Sun is stable today because it sits within the first level of this hierarchy. But it is not fundamentally stable forever. It is temporarily stable under current conditions. And those conditions are slowly changing. Over the next several billion years, the Sun will transition through each stage of this hierarchy, from hydrogen fusion to shell fusion to red giant expansion to core contraction, and eventually to a white dwarf remnant, a small, dense object slowly cooling over trillions of years. At that point, nearly all internal activity will cease. No fusion, no convection, no sustained energy production. Only residual heat slowly radiating into space. The Sun as we know it will no longer exist. But even this endpoint is not the deepest part of the story. Because behind all of these transformations lies a more fundamental question. Why does the universe allow this entire sequence of stable and unstable phases at all? Why do physical laws permit objects that can resist gravity for billions of years? Why do quantum rules exist that prevent matter from collapsing endlessly? Why does energy behave in a way that allows temporary balance instead of immediate chaos or immediate collapse? At this level, we are no longer just describing the Sun.
We are describing the structure of physical law itself. And that structure appears to sit precisely at the boundary between instability and stability. A universe too different in its constants might never produce stars. A universe too extreme in its forces might produce only short-lived explosions or eternal collapse. But our universe appears tuned to allow something unusual. Long-lived, self-regulating, energy-producing structures that persist across cosmic time. The Sun is one example of that possibility. Not the explanation, just the evidence that such a balance can exist. At this point, it may seem as though we have answered the question. The Sun is stable because gravity pulls inward while pressure pushes outward. Fusion regulates itself through feedback mechanisms. Quantum mechanics provides additional forms of support when necessary. Case closed. But that answer only explains how the sun remains stable once it already exists. It does not explain why a stable star exists in the first place. And that distinction is important, because the existence of a stable star is far from inevitable. Long before the sun began shining, there was no star. There was only a vast cloud of gas drifting through space. Mostly hydrogen, mostly darkness. No core, no fusion, no sunlight, no planets, nothing that remotely resembled the solar system. For the sun to exist, that cloud first had to collapse.
Gravity again became the driving force. Tiny fluctuations in density caused certain regions to contain slightly more matter than their surroundings. Those denser regions exerted slightly stronger gravitational attraction. More matter fell inward. The regions grew denser still. A positive feedback loop emerged. Small differences became larger differences. Eventually, entire clouds began contracting. Yet even this process encounters an obstacle. If gravity were the only factor, every cloud would simply collapse directly inward. But nature introduces another complication: angular momentum. Anyone who has watched an ice skater spin has seen the principle in action. As the skater pulls their arms inward, the rotation speeds up. The same thing happens in collapsing gas clouds. Even an extremely slow initial rotation becomes amplified as the cloud shrinks.
The result is that matter does not fall straight toward the center. Instead, it begins orbiting, flattening, spreading into a rotating disk. This disk becomes one of the defining features of star formation. The young sun formed at the center. The planets eventually emerged from material remaining in the surrounding disk. What is remarkable is that stability begins appearing before the star is even born. Gravity tries to pull everything inward. Angular momentum resists direct collapse. Magnetic fields influence motion. Radiation pushes outward. Turbulence redistributes energy. Every stage involves competing effects balancing one another. The universe seems remarkably good at creating order through opposition. Again and again, stable structures emerge not because one force dominates, but because multiple forces compete. This principle appears everywhere. Planets exist because gravity and motion balance.
Stars exist because gravity and pressure balance. Galaxies exist because attraction and motion balance. Even atoms exist because electromagnetic attraction and quantum behavior balance. Reality itself appears filled with dynamic compromises. And perhaps nowhere is this clearer than in stars. When astrophysicists simulate alternative universes with different physical constants, something intriguing emerges. Many hypothetical universes do not produce stars resembling our sun. Some produce stars that burn too quickly. Others produce stars that never ignite. Still others create radically different stellar populations. The precise details remain an active area of research, but the broader lesson is difficult to ignore. Long-lived stars depend on a surprisingly intricate combination of physical laws. The sun is not merely a ball of gas. It is the outcome of numerous constraints operating simultaneously. Gravity must be strong enough to form stars, but not so strong that stars burn through their fuel immediately. Nuclear reactions must occur, but not so rapidly that stability disappears. Quantum mechanics must permit tunneling, but not so efficiently that fusion becomes explosive. The strong nuclear force must bind nuclei, but within ranges that allow complex stellar chemistry. Again and again, we encounter a recurring pattern.
And that bridge becomes even more fascinating when we examine the nature of energy itself. Every second, sunlight spreads outward into space. Some reaches Earth. Some reaches distant planets. Most disappears into the vast darkness between stars. The sun is constantly losing energy, and yet it remains stable. How can that be? The answer lies in the continual conversion of mass into energy. The sun is slowly consuming itself. Not dramatically, not catastrophically, but continuously. The sunlight illuminating a tree, the warmth on a summer afternoon, the energy stored in food through photosynthesis. All of it ultimately originates from a gradual reduction in the sun's mass. The process is so slow that the sun can continue for billions of years. But the principle is profound. Stability is not achieved by preserving everything unchanged. Stability is achieved through controlled transformation.
The sun survives because it changes. It remains constant because it evolves. This idea appears paradoxical at first, yet it may be one of the deepest lessons in nature. Nothing remains stable by remaining frozen. Stability emerges through adaptation, through balance, through continual adjustment. The sun's apparent permanence is actually the result of ongoing change operating at a rate so slow that human perception mistakes it for constancy. And perhaps that is why the sun has fascinated humanity for thousands of years. Ancient civilizations saw it as a god, a symbol of permanence, a source of life. Modern science removed the mythology, but in doing so, it uncovered something equally awe-inspiring. The sun is not a simple object. It is a self-regulating nuclear system governed by gravity, quantum mechanics, thermodynamics, electromagnetism, and nuclear physics simultaneously. It is one of the most successful balancing acts known to science. For nearly 5 billion years, gravity has attempted to compress it. For nearly 5 billion years, energy generated in its core has resisted that compression. Neither side has achieved complete victory. The result is the star that made Earth possible, the star that powers every ecosystem, the star whose light carries the history of nuclear reactions occurring deep within a region no human will ever visit. Yet the most remarkable part of the story may be this. The sun does not remain stable because nature prefers stability. Nature often creates instability. Explosions occur, stars die, galaxies collide. The sun survives because it changes. It remains constant because it evolves. This idea appears paradoxical at first, yet it may be one of the deepest lessons in nature. Nothing remains stable by remaining frozen. Stability emerges through adaptation, through balance, through continual adjustment. The sun's apparent permanence is actually the result of ongoing change operating at a rate so slow that human perception mistakes it for constancy. And perhaps that is why the sun has fascinated humanity for thousands of years. Ancient civilizations saw it as a god, a symbol of permanence, a source of life. Modern science removed the mythology, but in doing so, it uncovered something equally awe-inspiring. The sun is not a simple object. It is a self-regulating nuclear system governed by gravity, quantum mechanics, thermodynamics, electromagnetism, and nuclear physics simultaneously. It is one of the most successful balancing acts known to science. For nearly 5 billion years, gravity has attempted to compress it. For nearly 5 billion years, energy generated in its core has resisted that compression. Neither side has achieved complete victory. The result is the star that made Earth possible, the star that powers every ecosystem, the star whose light carries the history of nuclear reactions occurring deep within a region no human will ever visit. Yet the most remarkable part of the story may be this. The sun does not remain stable because nature prefers stability. Nature often creates instability. Explosions occur, stars die, galaxies collide.
Black holes consume matter. Entropy relentlessly increases. And still, within that restless universe, islands of temporary order emerge. Stars, planets, life, conscious observers, structures capable of existing long enough to wonder how they came to be. The sun is one such island, a temporary victory against chaos, a balance point maintained by physical laws acting across scales, from quantum particles to stellar dimensions. And perhaps that is the deepest answer to our original question. Why is the sun so stable? Not because stability is guaranteed. Not because the universe was designed to make stars easy. But because the laws of nature allow a remarkable equilibrium to emerge between opposing tendencies. Gravity pulls inward. Pressure pushes outward. Fusion consumes fuel. Quantum mechanics enables fusion to occur. Feedback mechanisms correct deviations. Evolution proceeds slowly enough to preserve balance for billions of years. The sun exists at the intersection of all these processes.
A star suspended between collapse and explosion, between permanence and change, between order and chaos. And every sunrise is a reminder that this balance, however temporary on cosmic timescales, has endured long enough for a planet to form, for life to evolve, and for conscious minds to finally look upward and ask one of the most beautiful questions in science. Why does this star continue to shine? After more than a century of modern astrophysics, the answer is richer than anyone imagined. The sun shines because the deepest laws of the universe permit it, and its stability is the visible consequence of some of the most extraordinary balances ever discovered in nature. A star suspended between collapse and explosion, between permanence and change, between order and chaos. And every sunrise is a reminder that this balance, however temporary on cosmic timescales, has endured long enough for a planet to form, for life to evolve, and for conscious minds to finally look upward and ask one of the most beautiful questions in science. Why does this star continue to shine? After more than a century of modern astrophysics, the answer is richer than anyone imagined. The sun shines because the deepest laws of the universe permit it, and its stability is the visible consequence of some of the most extraordinary balances ever discovered in nature.